Hi everybody, welcome back to the second of 3 videos for our Dual Unknown Lab. And here again are the 3 main concepts we're going to cover in the Dual Unknown Lab. And this video is going to look specifically at FTIR, otherwise known as Fourier Transform Infrared Spectroscopy. So I thought I'd show you what our actual IR looks like in our Orgo lab. This is the actual instrument. And here is a student who is actually running their liquid sample, their pure organic sample. This is not an aqueous solution, but that's their pure liquid sample on our ATR FTIR instrument. They're very cool, and I hope someday that you'll be able to get into the lab and play with them. This is then it goes to an instrument, goes to a computer, which then processes the data. And if you wait just a few seconds, in just a second, up pops what looks like our FTIR, otherwise known as IR spectrum. So you're gonna get this data for the dual unknown. Sadly, you won't be able to run your own, but I'll supply you with this data for each unknown. But I want you to understand what you're actually looking at, and that's what this brief video is all about. So here are 2 organic compounds, basically the same compound in slightly different forms. And from the last video, you should recognize how they differ and how they actually got from one to the other. But in IR is really only looking at covalently bonded molecules. And it is really cool in that it'll help us understand different functional groups, like ones in this molecule that have so many different functional groups. But what we need to be really clear about is that IR loves covalent bonds, but it absolutely hates, bleh, can't even see if your molecule is charged, the IR will not be able to detect it. So that's why in that last little movie clip, you were looking at a student using their pure organic liquid, uncharged, and using it on the infrared spectrophotometer. So let's take a look at why it loves covalent bonds a little bit. And I do mean a little bit, okay? Just to give you a little flavor of what's happening. And then I'll refer you to other places you can go if you want to dive deeper into the theory of how infrared spectroscopy works. Or you can take our physical chemistry class and learn more there too. So infrared radiation is really interested in covalent bonds because when a bond changes its dipole moment and stretches or bends to do this, this little energy stretch and bend is actually what the infrared radiation is causing the molecule to do. And actually in doing a bend or a stretch, you're going to change the direction and the size of a dipole moment of that molecule. And when that happens, it will absorb the infrared radiation needed to cause that specific stretch or bend. Oh, got it? Oh, that's it. That's the theory part. Keep in mind the region that we use is from 4,000 to 600 inverse centimeters. Inverse centimeters is a weird little frequency, but it's the most common one that's used in IR, so we'll have to adapt to. Why should you care about IR? Just because it's going to help you solve your dual unknowns? Well, maybe it could help you solve other situations as well. Like, hey, I have these 3 white solids and I'm not quite sure which one is caffeine, which one is dopamine, and which one is morphine. Okay, this could matter in your world. So, notice the infrared spectra for these 3 compounds. These look very different. And the first thing I want you to notice is that what we call an absorption in IR is actually a peak that goes down. So peaks that go down are absorptions in the IR. And from left to right, it goes from 4,000 on the left to 600 inverse centimeters on the x-axis. Okay, so the furthest left is 4,000 inverse centimeters, furthest right. And notice that in all of these, on the right-hand side of the spectra, it looks really busy. A lot of peaks pointing down, tons of stuff. And I want to let you know right now, you could cut this IR essentially in half and throw that noisy section away, because we will never analyze that noisy, heavy peak section. Yes. Woohoo! Why will we never analyze that piece? Because the information that's coming out in that region is redundant to the same information we can get out in the higher region. So we don't need to get that kind of redundancy built into our dual unknown labs. All right. If you become an IR expert, then yes, you'll go venture into that weird little, 600 inverse centimeter region and try to detect things, but it's very hard. So, as I mentioned, IR is looking at covalent bonds or polar covalent bonds that stretch or bend. And these are the two most common vibrations that cause a change in dipole moment. And this picture here is a screenshot of a program that I recommended that you download. It's called IR Tutor. And the best part about IR Tutor is you can click on this compound toluene, which is a CH3 attached to a benzene. You can see it in the upper, the upper left-hand corner, if I'm pointing the right way. But then you can actually take this program and click on any one of the peaks to actually demonstrate what is causing that peak. So what I like about this is I can click on this peak just below 3000. It's specifically 2872. That's very specific, but it's showing you the CH stretches that are causing a change in dipole and are causing an absorption of infrared radiation. So if we have an sp3 hybridized CH bond, like this one here, this is where we will always see a CH stretch and an absorption in IR. So it will help us tell if we have alkanes in our molecule. We can get even more, oops, let me go back. I don't know what happened to it. Wait, where'd you go? Oh, I think it disappeared. Okay. Here it is. Technical glitches, yes. This is the peak at 1483, so you can click on that one. And I just wanted to show you this one because this is the same CH piece of the molecule, but the two H's, instead of stretching, they're bending, as you can see. So I like how this program animates the types of stretches and bends that are causing the absorptions. It's kind of fun. And then you can always go click at those peaks way down below on the right, bottom of the IR and see what kind of wild stretches and bends that are going on there. We have wags, there's such a thing as wagging in IR. It's pretty cool. That program I'm talking about is called the IR Tutor program. It's a free program, yay, free program from Columbia University. And if you just go to this website over here, you'll be able to get that program. And I highly recommend it as just a way for you to look at different functional groups and different bonds and see where they absorb. Not to mention, it's kind of fun to animate them. It goes a little crazy. So here is a typical IR spectrum again. This one is of cyclohexanone. It has a C double bond O. And as you start to learn your functional groups, hopefully you recognize this as a ketone. This ketone is attached to a ring, but it is not a benzene ring, it is an alkane ring because I don't have double bonds anywhere around it. So even though it's a 6-membered ring, it's just a bunch of alkanes. So I can see that from its IR, that there are peaks right below 3000 over there that are indicative of a CH-sp3 bond. I can see a C double bond O somewhere in the region of 1750 to 1625. That region just has to have a peak coming down somewhere to help me see a C double bond O. And again, I'm reminding you, do not look at that lower region. Ugh, too messy, you don't need it. It is called the fingerprint region. If I have an OH or an NH in my molecule, they like to live much higher, like an alcohol and amines and amides. They all live way, 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 way up there around 36 to 3200. And then you can see sp2 CHs off of double bonds are just to the left of 3000 at a little over 3000. Okay, these are the main bonds that slash functional groups we're going to have you understand and be responsible for and kind of know. But you will always have a literature table at your disposal for the dual unknown lab. This literature table is in our appendix of the Google site lab manual. So please take a look at it. Please feel free to copy and paste it and put it into any document you want. And it shows you where these literature absorptions should show up for very specific functional groups. And what I want to make really clear, hopefully really clear, is that if, for example, I have a C double bond O showing up in my IR, the only way I can differentiate that from a ketone from an aldehyde is I need to look, for example, for all the other types of absorptions that aldehydes have. Aldehydes have 3 total absorptions that they should have because aldehydes have this unique little CH bond. If I don't see those aldehyde peaks, then it's most likely a ketone or an amide or some other functional group besides an aldehyde. So please make sure that you spy all the bands. And this is only a partial table, as you can see from the title. All right, practice, practice, practice. Woohoo! The more we do it, the better we get. So here are some very fun compounds that are all organic. None of them are charged. And you might want to be able to tell the difference between some of these. So take a few seconds, see if you can identify which one of these would not show an absorption around 1700 inverse centimeters. And therefore, we could differentiate it from all the others. Okay? Pause the video if you want, because the answer is coming in 2, 1. Ready? All right, here comes the answer. That 1700 region, I think here comes the answer. There it is. That 1700 region is where we spy our C double bond O, otherwise known as a carbonyl. A lot of nomenclature, I know. But the C double bond O is at 1700-ish, and nothing else really lives there. So this compound must be ecstasy. So now I can tell them if I have ecstasy versus LSD versus any of these other kind of fun, weird drugs. All right. So this is the really useful tool, and it should help you identify what functional groups are on your dual unknowns. So please download your IR spectrum from the resources section of our Google site, and make sure you download the correct unknown IR for your IR compound. Because if you have the wrong IR for the wrong compound, life is going to get very, very, very bad for you. So, okay. And again, shoot me an email, shoot me a message, Zoom anytime if you have any questions at all. All right. See you later, everybody.